Okay, so yeah, thanks the organizer for giving me this opportunity. I am going to talk about yet another variation of the elephant random walk. And this talk is based on joint work with my PhD supervisors, Professor Kishanu Maulik of ISI Kolkata and Prathani Roy of IIT Bombay. So I will just again briefly go through the dynamics of the classical elephant random walk, but I think we all probably by now know these dynamics. So this was introduced by Scooch and Frimper in 2004. And this work starts from the origin, and then the elephant take the step +1 with probability q, or take the step -1 with probability 1 minus q. So if we denote the location of the elephant at time n by Sn, then we have that S0 is 0, and then S1 is S0 plus x1, which is a Rademacher Q random variable. And after that, the elephant chooses one of the past steps uniformly at random, and then it repeats the chosen past step with probability p, or takes the opposite step with probability 1 minus p. So we can write these dynamics in this another kind of way. So suppose un plus 1 be the index of the uniformly chosen past step. So it is a uniform random variable on 1 to n. And then suppose alpha n plus 1 be a Rademacher p random variable. Then the location of the walk at time n plus 1, Sn plus 1, is the location at time n Sn plus the n plus 1 step xn plus 1, where xn plus 1 is alpha n plus 1 times x un plus 1. Here this x un plus 1 is the uniformly chosen past step, and alpha n plus 1 captures the fact that the step is flipped with probability p or 1 minus p. So in statistical physics literature, this phenomenon is also termed as that to select past steps, the elephant has only one memory channel using which the elephant chooses, actually recalls its past steps, and the behavior of the memory channel is controlled by the Rademacher random variable alpha n plus 1, and the strength of the memory channel is determined by this variable p, or this parameter p. Now this is the classical elephant random walk, and in statistical physics literature, variation of this walk is considered, and in that generalization, the elephant instead of one has two in distinct and independent memory channels. So that basically means that instead of choosing one past step at random, the elephant independently and with replacement choose two past steps at random from all the previous steps. Now, this generalization has various applications. It has application in population dynamics model, where there are multiple competing species, or it is also has use in analysis of systems where there are long-range memory, and also it has in applications in opinion dynamics model. Now, from in the rest of the talk, I will denote the location of the elephant at time n in this walk by Sn, and the nth step will be denoted by xn, and as we will see here, xn can take three possible values, -1, 0, or 1, where 0 basically means that the elephant does not move at that time. And obviously Sn plus 1, the location at time n plus 1 is the location at time n plus xn plus 1, the n plus 1th step. So this is the dynamics of the walk. So the walk starts as usually from the origin, and both the first and the second steps, they are ±1 with equal probabilities. That is, they are basically Rademacher half, and they are also independent of each other. So as I said, that the first step is x1 and the second step is x2, and x1, x2 are IID Rademacher half. Now at time n plus 1, instead of 1, two past steps are chosen at random from the past steps, and they are chosen independently and with replacement. So both the chosen past steps can be actually the same steps. So let u1 n plus 1 be the index of the first chosen past step, and u2 n plus 1 be the index of the second chosen past step. And by our dynamics, u1 n plus 1 and u2 n plus 1, they are IID uniform on 1 to n. Now, since the elephant has two memory channels, so that behavior of the two memory channels are controlled by, instead of one, two different Rademacher random variable, which we denoted by alpha 1 n plus 1 and alpha 2 n plus 1, and they are IID Rademacher p random variable. Here p is the parameter of this walk. And through these two memory channel, So recall that the classical elephant random walk, the elephant has one memory channel and it recalls one sparse steps, which we denote, which we can write by alpha n plus 1 times xu n plus 1. But in this case, since there are two memory channels, the elephant recalls two past steps. xu1 n plus 1 is the chosen sparse step by the first memory channel. xu2 n plus 1 is the chosen sparse step by the second memory channel. But there are also some kind of flips happening as in the classical random walk. So ultimately, the elephant recalls the step by the first memory channel is given by x1 n plus 1, which is alpha 1 n plus 1 times xu1 n plus 1. And the step recalled by the elephant through the second memory channel is x2 n plus 1, which is alpha 2 n plus 1 times xu2 n plus 1. So this is an immediate generalization of the fact that is happening in the classical one memory channel elephant random walk case. Now, after recalling the two steps, x1 n plus 1 and x2 n plus 1, the elephant takes the majority step. So what is the majority step? Now, suppose the elephant chooses both the chosen steps are plus 1, then the elephant takes a step plus 1. If both the chosen steps are minus 1, then the elephant takes a step minus 1. Now, if one of the chosen step is plus 1 and another step is minus 1, then the elephant does not move. That is, the elephant takes a 0 step. And if one of the chosen sparse step is 0, then the step is determined by the nature of the another chosen sparse step. So if the elephant chooses one step as plus 1 and another step as plus 0, then the step is plus 1. If the elephant choose one step as minus 1 and another step as plus 0, 0, then the elephant takes the step minus 1. And if both the chosen step are 0, then the elephant takes a 0 step. That is, the elephant does not move. So any question regarding the dynamics of the model?
One small question, probably the answer should be clear, but is it obvious that you cannot translate this into an original majority elephant random walk with only one channel? Probably not, but how do I see that would not be possible? That this would be a hidden form of something simpler.
Right, that's a good question. But of course, one distinction is that in the classical one-channel case, there is no possibility of taking a 0 step. There are variations of that, of course. Maybe that's one possible reason, but I have not think about it. Yeah. Okay, so this model was originally proposed in the statistical physics literature by Shah in 2022, and in that paper, it was basically conjectured that the variance of the location of the walk, that is the variance of Sn, basically exhibit different behavior for different values of p. So if p is less than equal to 0.68, then the variance is of order n. If p is in between 0.68 and 0.88, then the variance is of order n to the power 8 times 2p minus 1 by 3. And if p is greater than or equal to 0.88, then the variance is of order n square. But this was all essentially our conjectures given in that paper. And it was also shown in that paper that the walk can be embedded in a certain type of earned model with multiple drawings. And also in literature, there exists some closely related walk which was introduced by Franchini in 2022, which is known as the elephant random walk with multiple extraction. So these are some of the related works from where our model is essentially motivated. Okay. Now, in the rest of the talk, I will describe the asymptotic behavior of this random walk. Okay, so let denote by Sn plus be the number of plus 1 steps taken till time n, and Sn minus 1 be the number of minus 1 steps taken till time n. Then the location Sn is of course Sn plus minus Sn minus. And let denote gamma n be this vector, which is a scaled version of Sn plus and Sn minus 1 scaled by n. And so we can write Sn by n as a linear transform of this gamma n. Now it can be shown that this gamma n satisfies the recursion relation of this form, gamma n plus 1 equals to gamma n plus some function gamma of gamma n plus en plus 1 by n plus 1. Here en plus 1 is a martingale difference sequence, and gamma is a quadratic function from R2 to R2. And this gamma function actually depends on the memory parameter P. And such kind of recursion relations are known as stochastic approximation in the literature, and with drift gamma. I mean, this gamma is called the drift of the stochastic approximation. The en plus 1 is called the random noise, and this 1 by n plus 1, this factor is called the step size. So we can express this gamma as a stochastic approximation process with drift gamma, random noise n plus 1, and step size 1 by n plus 1. Now, under appropriate conditions on n plus 1 and gamma, and using existing results of stochastic approximation, we can show that this gamma n converges almost surely to a random variable gamma p, and the support of this random variable is given by this set dp, which is essentially the set of certain zeros of this function of this drift gamma with this additional property. And this property ensures that ensures some kind of stability of the zero of the root gamma. And in our case, we can show that for p less than 7 by 8, this cardinality of this set dp is 1, and for p greater than 7 by 8, the cardinality of this set dp is 2. Then, of course, a restatement of the previous result was the almost sure convergence of this work, which basically tells that Sn by n almost surely converges to a random variable lambda p, which is a constant Cp times a Rademacher half random variable. And this constant Cp is given by these equations. So for p less than 7 by 8, this Cp is essentially 0. And for p greater than 7 by 8, this Cp is given by these complicated expressions whose graph is shown here. So we can see that for p less than 7 by 8, Cp is essentially 0, and then it suddenly increases to 1 as p goes from 7 by 8 to 1. And so an immediate conclusion from this result is that for p greater than 7 by 8, this work is ballistic, because this random variable lambda p is essentially non-zero in this regime, and also this work is transient. Now, one remark that in the original paper by Saha in statistical physics literature, they conjectured the phase transition at 0.88, which is essentially the approximate value of the true value, which we discover, which is given by 7 by 8. Our next target is to study the fluctuations of the work around the almost sure limit, that is to study the quantity Sn by n minus lambda p. And the challenge in studying these fluctuation is that the existing results in stochastic approximation does not give us immediately give us the results about the behavior of these fluctuations. So we need to actually redo all the kind of stochastic approximations calculations and proofs for studying this fluctuation. And the key reason behind is that this lambda p is not constant in our case for certain values of p, and is actually a random variable. And that's where lies the main difficulty. And we have discovered that for these fluctuations exhibit different behavior for different values of p, and it actually undergoes 3 phase transition, unlike the classical elephant random walk where it actually undergoes 1 phase transition. So the first phase transition happens at p equal to 11 by 16, the second phase transition happens at p equal to 7 by 8, and the third phase transition happens in this irrational number, which is approximately 0.96. And just again another remark, this first 2 phase transition was also conjectured approximately in the statistical physics literature. As you may recall that in statistical physics paper, it was the first phase transition was conjectured at 0.68, which is essentially the approximate value of 11 by 16, the true value. And this 0.88 again is the approximate value of the true value, 7 by 8. And these 3 phase transitions actually results in 3 distinct regimes. So this is the first regime, which is for p less than 11/16 and for p greater than this 0.96 and 1 in this interval. And we call this regime the subcritical regime, or which is essentially actually some kind of diffusive regime for certain values of p. And in this regime, Sn by n minus lambda p is of order 1 by square root of n. And then the second regime is where the, p can take the value 11/16 or this number. This is the critical regime. And in this critical regime, the fluctuation is of order square root of log n by n. And this is the third regime where p is in between 11/16 and 7/8 and 7/8 and this number. And this is what we call the supercritical regime. In this regime, the fluctuation is of order 1 by n to the power yp, where yp is a function of p, but it is always less than half in this regime. So this essentially summarizes the behavior of the fluctuation. I will now try to briefly explain why this type of phase transition occurs and how we can prove this type of result. So recall that Sn by n is a linear transform of the quantity gamma n of this stochastic approximation gamma n. And so we can write this fluctuation again as a linear transform of gamma n minus gamma p, where gamma p is the almost sure limit of gamma n. So, yeah. Also, we will denote the Jacobian of this function drift of the stochastic approximation gamma n by j at gamma p. Now, so j is essentially the Jacobian of gamma at gamma p. Now, recall that this gamma p is random for certain values of p. So, this j is also random. But it turns out that the eigenstructure of this Jacobian g is not random at all. So, we will denote the non-random largest eigenvalue of this random j as lambda I, ith largest eigenvalue by lambda I, and the corresponding eigenvector by nu I. And so we can write the fluctuation Sn by n minus lambda p as a linear combination of v1 transpose gamma n minus gamma p and v2 transpose gamma n minus gamma p. And so to study the behavior of this fluctuation, our main target is to study these two terms of this linear combination individually. So we aim to study v1 transpose gamma n minus gamma p and v2 transpose gamma n minus gamma p. Where remember that vi is the eigenvector corresponding to the ith largest eigenvalue lambda I of the Jacobian j. Okay, now recall gamma n is again a stochastic approximation process with the martingale difference En, and based on the martingale difference En, we can construct a martingale Mn plus 1 in this way, where these Ans are essentially given by this sum, which is approximately of order log n. And remember, this is a vector valued martingale because there are these e to the power j, e to the power minus j, this kind of terms are involved. And also this ek plus 1 is a vector. And our target is to study gamma n minus gamma p. So we study Mn, and then we study the residual part, which we denote by delta n plus 1, which is gamma n minus gamma p minus Mn plus 1. So essentially the Vi transpose gamma n minus gamma p is Vi transpose Mn plus 1 and Vi transpose delta n plus 1, and we study these two terms individually. Okay, so now this Vi transpose Mn plus 1, which is a martingale constructed from this martingale difference sequence k plus 1, and the order of this martingale is given by, remember now, though Mn plus 1 is a vector martingale, this Vi transpose Mn plus 1 is a scalar martingale, and the order of this scalar martingale is given by the quadratic mean of the coefficient of these martingale difference sequences, essentially the square root of summation phi k square, where these phi k's are given by these quantities. So it depends on the ith largest eigenvalue of the Jacobian j. And as it turns out, the phase transition actually happens because of the difference of order of this summation phi k squares. And for lambda I less than minus half, and before minus half and after minus half, depending on the value of lambda I, this summation phi k square can actually take is actually of 3 possible order, and depending on that, essentially what we can show that this quantity vi transpose n plus 1 is of order 1 by square root n for lambda I less than minus half, is of order square root of log n by n for lambda I equal to minus half, and is of order n to the power lambda I for lambda I greater than minus half. So this essentially summarizes the order of magnitude of this martingale, and as we will see, the phase transition in the original gamma n minus gamma p happens because of this phase transition in this behavior of this martingale at lambda equals to minus half. And then we also need to study the order of the quantity delta n plus 1, which is the residual part, and for that we will use this recursion relation of the martingale, which is given by this, that vi transpose mn plus plus 1 is can be written as using this recursion relation in terms of vi transpose mn, and we will use the Taylor approximation of the drift function gamma. So remember, the gamma p is always the root of this drift gamma, so gamma of gamma p is 0, and so if we expand this gamma of gamma n around gamma p, we can ignore the first term, and we can again have this Jacobian times gamma n minus gamma p, and then the higher order terms. And using this Taylor expansion, we can essentially write vi transpose gamma of gamma n approximately as lambda I transpose vi transpose gamma n minus gamma p. This is essentially a first order Taylor approximation. And using these two recursion relation, what we can write, we can establish actually a recursion relation for this residual part delta n plus 1, and which is given by this equation that vi transpose delta n plus 1 is given by this way in terms of vi transpose delta n. And so the approximately vi transpose delta n plus 1 is given by this continued product, and whose order is essentially, we all know that into the power lambda I. So we have established the order of vi transpose mn plus 1 and the order of vi transpose delta n plus 1, and we can combine these two to get the order of vi transpose gamma n minus gamma p, which is essentially a sum of these two quantity. And so in this expression, we can see that depending on the value of lambda I, the order of this quantity can actually take 3 possible value, and the leading order will survive, which we can write in this way, that for lambda I less than minus half, vi transpose gamma n minus gamma p is order of 1 by square root n. For lambda equals to minus half, this is square root of log n by n, and for lambda greater than minus half, this is n to the power lambda I. And again, finally recall that the main quantity of interest, which is the fluctuation of the work around the limit, is essentially a linear combination of both the v1 transpose gamma n minus gamma p and v2 transpose gamma n minus gamma p. We have already established the behavior of vi transpose gamma n minus gamma p for I equal to 1 and 2. So we can combine these two and can get this ultimate phase transition depending on the value of the largest eigenvalue of the Jacobian J. So for lambda 1 less than minus half, this order is of 1 by square root n, that this is the leading order. For lambda 1 equals to minus half, this is square root of log n by n, and for lambda 1 greater than minus half, this is n to the power lambda 1. Now the largest eigenvalue of the Jacobian J is given by these two quantities. So for p less than 7 by 8, this is kind of a linear thing, and for p greater than 7 by 8, this is this complicated expression which is shown here. And we can see that at p equal to 11 by 16, this lambda 1 equals to minus half. Again at p equals to that irrational value, which is approximately 0.96, it is also again minus half, and at p equals to 7 by 8, it is actually 0. So we can write this lambda 1 less than minus half equivalently as p belonging to these two intervals. Lambda 1 equals to minus half is as p belonging to this set, and for lambda 1 greater than minus half, we can write as equivalently p belonging to these two intervals. And thus for different values of p, this fluctuation exhibits these three different order, which is essentially summarizes the phase transition of the fluctuations of the work. Right. So essentially, this is the result again, a restatement of the result. And again, here I have given the final expression for this quantity yp, we can see that this for p less than 7 by 8 and greater than 11 by 16, this is this linear quantity, and for p belonging to 7 by 8 and this number, this is given by this thing, which is whose graph is shown here. So now, so these are kind of essentially the order of these fluctuations, but if we carefully study these two martingale, V1 transpose Mn plus 1 and V2 transpose Mn plus 1, we can actually get more detailed results for these fluctuations, which we actually did. And so these are some of those results. So this is the what we call the subcritical regime, that is p less than 11 by 16 and in between these two number. And in this regime, we have three types of result: one central limit theorem, one law of integral logarithm, and another quadratic strong law. And whose I mean, this kind of summarizes these three results, but I am not going into the detailed expressions of them. If you are interested, we can always talk later. But one important consequence of the law of integral logarithm is that in this regime, we can show as a consequence of this LIL that the work is recurrent here. This is the critical regime, P taking these two values. Here we also have three types of results: central limit theorem, law of integral logarithm, and quadratic strong law. And again, due to the consequence of LIL, we have that the work is recurrent, also recurrent in this regime. And this is the final regime, which is the supercritical regime, that P belonging to these two intervals. And here we don't have a traditional CLT, as we can often see in the elephant literature. So here the fluctuation is n by n minus lambda p, appropriately scaled by n to the power yp, converges almost surely to a finite random variable LP. And here this yp is the same yp as before, whose expression is given by here, is given here. Now, this almost all of our results, but there are two important open questions. We don't know anything about the behavior of the work at p equal to 7 by 8, and also we don't know anything about this random variable LP. And of course, any another more type of thing can be done here. For example, we can consider k memory channel instead of 2, or we can consider other variations of the classical elephant random work in this framework also. Those are all open. So this is some of the reference. So this is the paper where originally this work was proposed, random work with multiple memory channels. And the phase transition invariance was conjectured also in this paper. And this is the classical elephant random walk paper, the first paper. And this is a related paper, which is closely related to our work written by Cement Panching. So thank you. And if you have any questions, please feel free to ask.
Thank you. Questions? So you have all these, let's say, funny threshold values, etc. Is there a back of the envelope argument to see where they come from?
Yeah. So
I mean, there are solutions of some equation, but isn't there sort of that you can get more intuition for it other than just saying, okay, it's that? That's what I meant by back of the envelope.
Okay. I cannot say immediately that there are some kind of background intuition behind that, because all we know is that they're coming from that stochastic approximation equation, solving those kind of things. Yeah.
Each of them from like physics approximately what they should.
Yeah.
But like, what about for that value, right? 113 plus square root 97 over 128. Like, how do we get like that as the threshold for it going back to the subcritical regime?
So you are talking about
like that 113 plus square root 97, that 0.96 thing, right? Yeah. So like, I mean, like any intuition for like why is that the threshold for going back to the subcritical regime? At least for the first two, okay, some physicists kind of have the intuition for it, but like for this one, I mean it.
So I mean, you are essentially asking why again this going back to the critical regime after this threshold, right?
The subcritical regime.
Yeah, we don't have any intuition behind that. This is kind of a strange behavior, but we we suppose that this is happening because of, in this regime, this lambda p is actually random. And so this may be possible one of the reason why it actually deviates with the behavior with that of the classical random walk. Because in classical case, we always have this lambda p to be 0.
Okay, thank you.